Okay, onliners, can you hear me? Yes? Can you hear me?
Yes, sir.
Okay. তো তোমাদের কি ডিসিশন হলো কিছু জানো কি এখানে স্টুডেন্টরা কবে থেকে আসবে পার্মানেন্টলি? মানে ডিসেম্বর থেকে নাকি? হ্যাঁ, অফলাইনই ভালো। মানে তোমার কিছু কোয়েশ্চেন? So onliners, you have any question? হ্যাঁ হ্যাঁ, স্পিনার পাবে। আমি তো বললামই 2 ডাইমেনশনালে 2 কম্পোনেন্ট স্পিনার, 3 ডাইমেনশনালে 2 কম্পোনেন্ট স্পিনার, 4 ডাইমেনশনালে there will be 4 কম্পোনেন্ট স্পিনার, 5 ডাইমেনশনালে আবার 4। যেই বাড়তে থাকবে, বললাম না 2 টু দি পাওয়ার। হ্যাঁ, না না, স্পিনার গুলো কলম ম্যাট্রিক্স, তো গামা ম্যাট্রিক্স গুলো 4x4। হ্যাঁ, 3x3 ম্যাট্রিক্স, 3x3 সরি 2x2 হবে, 2x2, আর স্পিনার গুলো 2 কম্পোনেন্ট হবে। ওটা 3 ডাইমেনশন, তো ওটা অড ডাইমেনশনাল, এই জন্য ওখানে গামা 5 এর যে অ্যানালগ ওটা থাকবে না, ওটা খালি ইভেন ডাইমেনশনালি থাকে। হ্যাঁ, 3। হ্যাঁ, মানে ওখানে গামা 1, গামা 2, গামা 3 পর্যন্ত যাবে। হ্যাঁ, ওটা প্রোডাক্ট দিলে আবার ইয়ে হবে না, নতুন কিছু একটা দেবে না। মানে গামা 1, গামা 2 প্রোডাক্ট নিলে তো গামা 3 হচ্ছে, তুমি যদি আবার গামা 3 দিয়ে করো, গামা 3 স্কোয়ার 1 হয়ে যাবে। হ্যাঁ, এবং গামা 5 স্কোয়ার এখানে 1 হচ্ছে, ওখানে তাই হবে। হ্যাঁ হ্যাঁ, ওইভাবেই। টোটাল ডাইমেনশন মানে সিগনেচারের উপরে ডিপেন্ড করবে না, ওটা ক্লিফোর্ড অ্যালজেব্রা যেটা গামা মিউ গামা নিউ যেটা আছে অ্যান্টি কমুটেটর, ওখানে আসবে টুয়াইস ইটা মিউ নিউ, আর যদি ইউক্লিডিয়ান সিগনেচার টুয়াইস ডেল্টা মিউ নিউ, দ্যাটস অল, ওখানে চেঞ্জ হবে। সুতরাং গামা ম্যাট্রিক্সের রিপ্রেজেন্টেশনটা চেঞ্জ হবে, এবং চেঞ্জটা খুব সামান্য। মানে যেহেতু ধরো 1 -1 -1 করছি, ওখানে -1 বানাতে হলে ইউক্লিডিয়ান সিগনেচার থেকে গামাগুলোকে যদি আই বা গামা আই গুলো যেগুলো আছে স্পেশাল কম্পোনেন্ট, মাল্টিপ্লাই অল অফ দেম বাই আই, প্রোডাক্ট করলে একটা মাইনাস সাইন জেনারেট হবে। That will give you the gamma matrix for the Minkowski case. So from Euclidean case to Euclidean case, the transition is quite simple. Okay. So let me start kori. Okay. So today I'm going to talk about the physical plane wave solutions of Dirac equation. Is it visible what I have written for onliners?
Okay, sir.
Okay. So the Dirac equation that I have written down for you was p slash minus m acting on psi of x was 0. And p slash was, you remember, p slash is gamma mu, p P mu, and P mu is I del mu, right? That you know. I can write down P mu as I del mu because P mu is equal to I del mu. To split, consider mu equal to 0 component. So P0 is equal to I del 0, and for mu equal to I, it is Pi is equal to I del I. But this implies that Pi, if I raise the index, it will cost you a minus sign. This will be minus del I. Okay? So this is real momentum. The contravariant component of the real momentum. And for P0, there will be no change in sign. It will be just I del naught. You can write both ways. Because raising or lowering the time component, time index, so to say, will cost you no sign. Because the convention we have chosen is mostly negative. 1, minus 1, minus 1, minus 1. Okay? And always remember the contravariant components are actually the real components of momentum. You should remember this, not the covariant component. Because these are the components, contravariant component. When you take the non-relativistic limit, they give you the correct transformation property of this thing. Transformation of non-relativistic limit. So C tends to infinity limit. The covariant ones will not do. Then you ask, then what's wrong with covariant in the Galilean limit? The thing is that there is no space-time metric for Galilean space-time. There is a metric only in the spatial part, no space-time metric. Okay, so there is no metric to raise or lower indices. You start with the contravariant, but you do not have the covariant counterpart. Because in absence of the metric, you cannot lower the index. Okay, but you can do this in the case of relativistic situation. This is just to give you some this thing. So these things are well known to you, but just to remind you. In case. Huh? Oh, বড় করে. Okay. So this gamma mu p mu, or this thing, I can call it as a Dirac operator. Okay, p slash. Some people write it d slash also. The Dirac operator. So, but the Dirac operator, you see, is actually involves gamma mu now. In usual Schrodinger mechanics, when you did Schrodinger equation non-relativistic quantum mechanics for a spinless particle, you did not have any analog of gamma mu. You just have momentum is given by I del mu. Okay? But now you have this 4x4 matrices. And for I del mu, you know what are the planar solutions. Okay? Planar solutions can be two kind. Means P mu acting on e to the power I k dot x, or it will be what? So if you want to calculate this thing, so it will be P mu is by I del mu e to the power I k nu x nu. Let me write it this way. So when del mu acts on these things, exponential thing will come k nu x nu, and then if you differentiate, this thing will give you I times k nu delta nu mu, right? You differentiate this thing. So what you get? Huh?
Schrodinger ইকুয়েশনের ভিতরে কি কোথাও স্পিনের ইনফরমেশন থাকে না?
No, if you are dealing with spinless particle. If you have spinning particle, then you have two component spinners. Okay. These are SU2 spinner. Now they are SL2 spinners in relativistic situation. Okay. So you have k mu minus k mu e to the power I k dot x, that is a short. So minus k mu is the eigenvalue of this thing. Okay. Now you can do the same thing if you just replace k by minus k. So p mu e to the power minus I k dot x, you replace k by minus k, so it will be k mu e to the power minus I k dot x. Okay. So this is the eigenvalue. Now I am taking cannot to be greater than 0, positive quantity. So what happens is that this particular plane wave, if give you, because for the 0 index, as I told you, 0 if you raise or lower, it doesn't cost you any sign. So 0 index will give you minus k0, and k0 being positive, it will indicate this e to the power I k dot x corresponds to negative energy solution. Okay, e to the power I k dot x represents negative energy solutions. These are all plane wave solutions. Physical states will not be plane waves, as you know, because plane waves have sharply defined momentum. That you know from usual non-relativistic quantum mechanics itself. Physical states will be given by some wave packets, which will be obtained by superposing different plane waves, so that you have spread in momentum delta k. Here delta k is 0, uncertainty in momentum is 0. Okay, but there delta k for typical wave packets, when you superpose, you will get some finite spread. So correspondingly, you have finite spread in delta x also, which will necessarily satisfy the Heisenberg's uncertainty relation, delta x, delta x, that you know from your quantum mechanics. So here I am talking about just plane waves. I will talk about superpositions of states to form wave packets maybe later after lunch session. So for the time being, these are plane wave solutions, and e to the power minus I k dot x represents,
Sir,
yes.
I have a question that when we are lighting the the gamma mu, in the relativistic case, we have the information of spin induced here. But for the non-relativistic case, I can write the Schrodinger equation as h psi equal to e psi. So if h is p square by 2m, let's say a free particle, so p square by 2m acting on psi is I h cross del del t acting on psi. Okay, so now this p square can be written as sigma dot p times sigma dot p, right?
Yeah, that you can write, but you have to decide. You can mathematically write it, but then you have to decide on what kind of object it is acting on. Is it acting on some two-component spinner, or it is acting on some
Some scalar wave function. Yes.
So depending upon on what you want to act on, that is your Hilbert space. This is a Hilbert space of square integrable just one component functions, or it is a Hilbert space of square integrable spinners, two component spinners. That you have to decide right in the beginning. Only after this decision you have made, then you have to write your Dirac, your Lagrangian, your Hamiltonian in that fashion. Okay, so it will be dictated by that. Okay, so here I am just talking about the momentum part. So I am just visualizing as if it is doesn't have any speed. Okay, so this is a simple plane wave. So just to these things you have already learned, probably Shayan and but just to have some continuity, I am just reminding you. Okay, and e to the power of minus I k dot x represents positive energy solutions. Positive energy. . Okay. So now when you come to Dirac spinner, you have extra gamma mu. Okay. So this e to the power I k dot x, if you can superpose, you will get something, as I said, you can superpose, you can get what is called the packets, and they will typically belong to your square integrable functions. So you can superpose them and get a square integrable functions. Regarding gamma mu, so you can see that they act on different, means they act on a 4-component spinners, so their domains of actions are different. So typically a psi will have 4 components: psi 1x, psi 2x, psi 3x, psi 4x. Okay. Regarding p's will just act independently on these things. They will not mix up the, as I told you, under translation they behave like a scalar. I told you in the last class. So they just act on this and they don't mix up. But gamma mu's will mix up. So it is something like a tensor product that you have learned your differential geometry. So Dirac operator should actually be written as gamma mu tensor p mu. P mu act on square integrable functions. So P mu acts on means L2 of R1, 3 Minkowski space-time square integrable functions on this thing. Actually, not one, I should not. Functions should be defined on 3-dimensional spatial surface. Okay, square integrable functions on these things, and gamma mu's will act on the 4 components, on all the 4 components, all the 4 components together, thereby mixing them all. And P mu acts on these things, so and therefore acts on psi alpha, let me call it. These indices range from 1 to 4. Alpha acts individually. Okay. There is another way that you can see it. You can just just forget this I factor, just gamma mu del mu. You can think of it as some sort of, in differential geometry, when you write an exterior derivative of a function, remember it is written as dx mu del mu f. Okay. So gamma mu's are just a counterpart of dx mu's. Okay. So these are called, you can think of this as a Clifford valued one forms. So this d mu's, means forget this I factor, they can be thought of as Clifford valued one forms. Okay, that's what you have. I'll make it more clear. First of all, there is a similarity between dx mu and gamma mu's. There is a similarities and dissimilarities. As I told you in the Clifford algebra, just like any 2 by 2 matrices can be written as a linear combination of identity and Pauli matrices, Likewise, any 4 by 4 matrices can be written as a linear combination of the 16 Clifford matrices I have constructed. Remember, identity, gamma mu's, gamma 5, the sigma mu news, and etc. etc. Okay, I have listed all of them. So they span the 16-dimensional space for you. And if you write any algebra element in the 16-dimensional, if you take any algebra pair of such algebra elements and take their products, it will belong to the same space. Okay. So a vector space which is equipped with this kind of multiplication rule, this is an additional property. So a vector space which also enjoys the property that any pair of elements can be composed through multiplication to get another element in the same space, that is closed under multiplication rule. Such a vector space is called an algebra. Okay. So that's why I call it a Clifford algebra. It is generated by gamma mu's, an identity, and the span means generated by means you take all sorts of polynomials. Of course, you cannot go indefinitely, means after some point you just like sigma's case. If you take square, it becomes identity. For gamma mu's case, to get identity, you have to take 2 or 3 in power, means exponent twice or thrice kind of thing. But for all the Dirac matrices, means the 16 matrices that I have written down for you. Not all of them will be just equal to identity just by squaring. Some may be requiring to the cube kind of thing to get the identity. So anyway, the finite power will be required. So it forms an algebra under multiplication. So dx mu's also enjoy the same kind of property. I can take this is just a digression because you have studied differential geometry. I just wanted to link up these cases. Here also you can take one dx mu's will span say 4-dimensional space. Dx mu wedge dx mu, it will span 6-dimensional space. Dx mu wedge dx mu wedge dx lambda. It will again span 4-dimensional space. Okay, this is 1, this is 4, this is 6, this is again 4. And again, if you take the product of all 4, it will be just means dx0, dx1, wedge dx2, wedge dx3. Because all of them have to be distinct, so up to a constant, it will be equal to the 4 forms. And it will behave like a scalar, sort of, just one component. So you can count them. So this will be basically what?
It's like Hodge dual, right? N forms and n minus p forms, sir. It's like Hodge duals, no? The n forms and n minus p forms are having the same representation.
Yeah. Basically, this thing is the Hodge dual you have studied. Basically, the same thing. So you see, this is also 16-dimensional space. Gamma mu's also, as you can see, there will be 1 gamma mu. Then there will be sigma mu nu, which is gamma mu anti-commutator. And then you have the other things. And you have the ultimately here it is gamma 5. There is one 4-dimensional, what I have written, it's a gamma mu nu lambda. It will be actually again something like a Hodge dual of this thing.
So sigma mu nu is the commutator, no?
Yeah. Sigma mu is a commutator of gamma nu. So it makes it antisymmetric.
Yes.
So the basic algebra structure with underlying vector space is same. Only thing is the product rule is different. So if I take these things, dx mu wedge dx nu plus dx nu means interchange these things, dx mu, this is 0. For the Clifford case, it is gamma mu plus gamma mu, it is the twice eta mu. So this is the product rule is given by this. And here the product rule is this. So algebra wise means the almost same, means the underlying vector space is same, Okay, but the product rule is slightly different. That's the thing. Okay, this just to give you an idea how all these things relate to the differential geometry you have already learned. Okay. Okay. So now I have this thing, so I can write down my plane wave solutions as an n such, take this thing as n such. So write positive energy solutions to be e to the power minus I k dot x uk. Okay. UK. UKs are 4-component spinners written in momentum space. Here it is written in x space, coordinate space, so it is a momentum space. So this is the kind of plane wave solutions that you can expect. Okay. Likewise, for negative energy solutions, e to the power I k dot x vk. Negative energy solutions. Again, here you can see this UKs you expect because gamma mu's have to act on these UKs. P mu will act on this thing. Okay. P mu act on just functions. And gamma mu will act. So there should be some slot for gamma mu to act on. And that will be 4-component spinners. So this is analogous to when you study in Maxwell theory. You write A mu, right? A mu x. Also positive energy solution, you write e to the power minus I k dot x plus a x mu with some polarization index x mu k. Some polarization index you write. Right? So these are the polarization, this thing. So these are polarization vector and these are called polarization spinners. Okay, these are just analogous to that. Okay. So now you can just apply this thing p slash minus m. You can get these solutions. K slash minus m uk is equal to 0, and this thing will give you k slash plus m vk equal to 0. So you see, I am reserving this notation for positive energy solution, the polarization spinner, which occurs for the positive energy solution, and Vk, the polarization spinner, which occurs for the negative energy solution. Okay. So now, let me see how to construct such a spinner. One way of constructing, I have already shown you. You take a Lorentz boost SL2C transformation. Remember, in fact, this part I leave that as an exercise for you to do independently. But that I did is a chiral representation. Here I am doing the standard Dirac representation. They are simply related by unitary transformation, as I showed you last time. Okay, so you can go back and forth from one representation to another representation without any difficulty. Okay, so how to obtain this? The first strategy is to work out the structure of this U's and V's is the rest stream of the particle. I am considering particles with mass m, which is non-zero. Zero mass case, as I have discussed in the group theory class, they describe well spinner. They also become simple SL2C spinner, 2-component SL2C spinner. That I will discuss in detail later. For the time being, I am confining my attention to massive particles. Okay. So now the strategy is go to the rest stream. In the rest stream, what happens is that k slash becomes gamma mu k mu becomes gamma 0 k 0. and the rest frame. Okay. So what do you get? So you can write down gamma 0, k0, other terms will not survive, minus m, u, k refers to the rest frame. In the rest frame, the 4 vector k will be m, 3 vector will be 0, 3 vector. Whenever I put arrow overhead, it represents the 3 vector. The rest frame, the 3 component of the momentum, special component of the momentum will be 0. So that's what you expect. But in the rest frame again, k0 is just nothing but m. That's what I have written. So I can just write m and divide throughout by m. So I will have gamma 0 minus, this is, remember there is an identity here, acting on u m0 is equal to 0. Okay. And what was gamma 0? Gamma 0 was the standard ratio 1 minus 1. Gamma 0 is a 2 by 2 identity matrices. Okay. Okay. So you just subtract the identity, this part will go and this part will remain. So what you get is actually 0 and identity. I'm ignoring the overall minus sign, and u m0 will now have component, say u1, u2, u3, u4. Okay. So it shows that u3 means now you can multiply, you know, the block, when you multiply matrices, block diagonal structure, you can treat them as independent element by themselves. You know these things. So this means that u3, u4 will survive after multiplication, but u1, u2 will not survive. But this has to be equated to 0, so it implies that u3 and u4 has to vanish. u3 and 0 is equal to u4 and 0 is 0. Okay. So you have the spinners in the rest frame, u m0 মাল্টিপ্লাই করো তাহলে u3 u4 0 0 u3 u4 টা পাবে না, that will be equal to 0. উপরে দুটো কম্পোনেন্ট 0 0 আছেই, u3. Okay. So this will have structure like u1 m0, u2 m0. Okay. So you can, without loss of generality, you can, because they are just, you can write down these as u1 m0 1 0 0 0 plus u2 m0 0 1 0 0. So you can actually don't bother about this factor because it will be linear combination of this and this canonical basis, two-dimensional space. So you can, without loss of generality, take these as your basic spinors, because all other spinors will be obtained by linear combination of these things. So without loss of generality, I identify we write um0 is equal to just u1 m0. U m0 to be u1 m0 is 1 0 0 0, is just 1, and u2 m0 is equal to 0 1 0 0. Okay. Likewise, you can work out the V case. Likewise, which I leave as an exercise for you. Likewise, the V case, you can write down V1, but that will correspond to negative energy solution. Mind that. Then the sign of K slash plus M will be there. 0 will be 0 0 1 0. হ্যাঁ 3 আর 4 টা থাকবে। V2 M0 হ্যাঁ ওটা কি U1 U2, sorry I writing say U1 U2 হ্যাঁ অবন্তিকা তুমি আমাকে একটু পরে একটার পরে ফোন করো, আমি বেলুড়ে ক্লাস নিচ্ছি। হ্যাঁ
আচ্ছা আচ্ছা ঠিক আছে ঠিক আছে।
Okay, so 0 0 0 1. না না আমি তো দুটোকে আলাদা ক্লাস করেছি না, একটা ইউ একটা ভি। ইউটা বলছি পজিটিভ এনার্জির জন্য আর ভিটা বলছি নেগেটিভ এনার্জির জন্য। আচ্ছা U3 U4 লিখেছিলাম, ওটাকে আমি নতুন নামকরণ করছি V1 V2। হ্যাঁ কারণ আমার সলিউশন ইকুয়েশন যেটা ছিল K slash minus M UK is equal to 0 and K slash plus M VK equal to 0, এই দুটো ইকুয়েশন ছিল না। মানে U1 এর যখন U1 করছি তার সলিউশন U1 U2 U3 U4 লিখছি, V1 এর জন্য যখন আবার করব V1 V2 V3 V4 লিখবো। যখন রেস্ট্রিমে চলে যাব দেখবো V1 V2 0 হয়ে যাচ্ছে, V3 আর V4 টা সার্ভাইভ করছে। So it can write as a linear combination of these things. Okay. So these are the solutions in arbitrary frames. Okay. Now there are two ways, as I told you, give a Lorentz boost, so rewrite these spinors in the chiral basis. It is not difficult. You can actually, right from the beginning, you can work in the chiral representation. Okay, you can get hold of spinors and give a Lorentz boost e to the power half sigma dot phi, remember, or minus phi, whatever it is. You can get the corresponding expression in arbitrary Lorentz frame. এটা একটু ছেড়ে দাও তো, arbitrary Lorentz frame. Here I am taking a different method. I leave that part as an exercise for you. Please note down that. Okay.
So what is the main difference behind choosing the while representation ones and Dirac representation ones?
কি বুঝলাম না তোমার কি বললে?
Why it is, I mean, why we are choosing while representation ones and the Dirac representation ones? I mean,
No.
whichever is suitable.
Whichever means your context will dictate whichever is suitable for you. Okay. Here I am working with the Dirac representation. You will see that there are certain advantages and certain disadvantages. A complementary case is of Carrel representation, where there are again certain disadvantages and advantages. So these things will be dictated by the context. Okay. So here mostly I am working with the standard Dirac representation. Okay. So now I have this pair of equations k slash minus m uk is equal to 0, right? This is a equation. It should satisfy an arbitrary Lorentz frame. So I can write down uk because the moment k slash minus m acts on it, it should give 0. So you can expect that should give me some k slash plus m divided by something which I am not specifying now, acting on your restraint spinner u alpha, let me call it u alpha m0. Okay. And this is the
Sir,
u alpha. So alpha varies from 1 to 4, 1, 2, 3, 4. This is the solution. I can easily guess that it has to be, because the moment k slash minus m acts on this thing, you see k slash minus m into k slash plus m will be 0. Remember, it will be just like a square minus b square formula, k slash square minus m square, which is a slash square is a square, I proved last time. So k slash square will be k square, which is m square from Einstein's energy momentum relation. So this will vanish. So you can immediately guess that what will be the prefactor sitting in, except that it's normalization. So I'm telling you what is the normalization well in advance. You can really verify that it really satisfies the orthonormality condition as desired. It is actually, you can put something arbitrary and demand that orthonormality condition will be satisfied by all this A alpha. But here I'm telling you in advance, and you can write down, check, verify it later. Okay? Yes. Let me write down. There are 4 independent solutions, right? Means U1, U2, U3, U4. In the rest frame, I got 2 independent solutions which are vanishing, 2 independent solutions which were top component was 1, another at top, the second component was 1. There are 2 independent non-vanishing solutions, other 2 independent vanishing solutions. Now, arbitrary frame, you expect that all the components will be non-vanishing in general. Okay, because the gammas will act and they mix up the components, as I told you. Okay, it takes only that simple form in the rest frame, in no other frame. Okay, so this is alpha component will be like this, that you expect, because the moment k slash minus m acts on this thing, so k slash minus m will multiply this thing. So k slash minus m into k slash plus m will be 0. That's what proved last time. Okay. So this just by simple inspection you can write down like this. And further, this normalization condition, I'll verify that it indeed that the job is required to ensure that orthonormality condition is preserved. But you can check some simple things. You go to the rest frame. In the rest frame, energy will be the mass itself. U will be mass itself. So it will be 2m. 2m into 2m whole squares. Under square root, it will be 2m. Right? In the rest frame, it will be again gamma 0 k0. K0 will be mass again. Right? So again, mass will add it up. 2m will cancel. You will get 1. Right? And you will get back the rest frame result. Okay. খাওয়ার ব্যবস্থা হবে কি? হ্যাঁ হ্যাঁ আচ্ছা আমি এক মিনিট একটু ওখানে দাঁড়িয়ে আছে, ও একটু ঘুরে ফিরে বেড়াচ্ছে বোধহয়, দেখি আমি। আজকে কি মঠেরই পুজো হচ্ছে? আচ্ছা হ্যাঁ ঘোষবাবু, বলছি কি আজকে ওইখানে সামনে একটা জগদ্ধাত্রী পুজো হচ্ছে, ওই সারদা পীঠ, ওখানে বোধহয় ভোগ পাবেন। এখন দিচ্ছে? এখনো দিচ্ছে বোধহয়। হ্যাঁ সারদা পীঠের ওখানটায়, হ্যাঁ ওখানে ভোগ দিচ্ছে, একটু খেয়ে নেবেন। হুম ঠিক আছে। ঠিক আছে, any question? Okay. So arbitrary frame, it is like this. So how does it look like? Huh? রেস্ট ফ্রেমে হ্যাঁ করছে, কিন্তু এটা আলফা 1 আর আলফা 2 খালি সার্ভাইভ করবে। মানে রেস্ট ফ্রেমে মানে এরকম দেখো, আমি লিখতে পারি m0, this will be delta alpha 1, delta alpha 2, and 0 0. This will be your this thing. হ্যাঁ exactly, that's what I am telling. তুমি যদি gamma 0 m মানে তুমি you just work out gamma 0 k0 is m itself. So m gamma 0 plus 1 identity, this is identity matrix. Okay, আর নিচেও তোমার m থাকলো, মানে this is m 2m, right? This acting on u alpha m0. তুমি কি প্রশ্ন করছিলে? আচ্ছা তুমি বুঝে গেছো তো? Okay, so let me work it out in detail in the arbitrary frame. So this will be 1 by root over 2m m plus e gamma mu k mu plus m, and you write these things delta alpha 1, delta alpha 2. This for simplicity I can write down, I can use the notation phi alpha m0 and 0. For simplicity. Okay, so now this I can write down this as phi alpha m0 and 0 like this, where phi alpha is two component object like this, delta alpha 1, alpha 2, this is phi alpha. Okay. And this is again two component 0. Okay. So now if you just carry out the calculation, this is not difficult. I'll just write this thing. It is a simple thing. You can see that it will turn out to be. Please do the intermediate steps on your own. E plus k by 2m phi alpha m0 and sigma dot k u alpha k is like this. You just do it. Now you see that this third and fourth component also will survive. In the rest frame, this k3 vector is 0, it doesn't survive. Okay. It is a straightforward calculation. You just expand it, gamma 0, k 0, and this k vector, so k down will be k0, the 0th component, and the special component will be minus k. Mind that, because the lower component. You have to raise it and then identify it the k vector. Remember this. Okay. So now with this, I can calculate the u bar. Okay. U bar is what? U alpha dagger k gamma naught.
Sir, so the above expression is for the massive spinners in Dirac representation.
Huh?
The above representation is for the Dirac spinners in massive for massive
Yeah,
cases, right?
I'm talking about the massive case, as I told you a couple of times.
Okay, so if we just take the m goes to 0 limit, I mean the
No,
Lorentz boost.
it can be tricky.
Yeah, because I can't see that it is going to the wild spinners if we take m goes to 0 limit.
Sometimes you can take it correctly, means you can get the expected results. Sometimes you will not get expected results. Okay, you should be careful in taking this limit. In physics, this kind of limiting process is not very well defined all the time. You have to be very careful. Okay, but I'll come to that later. For the time being, I'm just considering massive case. Okay. So now you have to calculate this. So u alpha dagger k, u alpha dagger k is this thing. You just
স্যার বলছি ইউ আলফা m0 যেটা ছিল ওটা তো 4 কম্পোনেন্ট ছিল, ওটাকে 2 কম্পোনেন্ট করা হলো কেন?
কোনটা কোনটা বুঝলাম না, আবার বলো। হ্যাঁ হ্যাঁ, এটা just compact notation, because I'm dealing with here this matrices. When you write, there will be blocks of the sigma matrices will come, poly matrices. So you will get the poly matrices will act on two component spinners, so the top two components or the bottom two components. So you can get the 4x4 matrix partitioned into 4 compartments of 2x2 matrices, and then they will act on top two components or the bottom two components. So it's better and convenient to segregate them as something non-vanishing phi alpha m0 here and 0 here. Okay,
Okay, sir.
just for simplicity of manipulation. Okay, so now if you just do it, u alpha, so you again start from here, say you can either do it from here or here. For here, for example, if you do it, u alpha m0 dagger, k slash dagger plus m divided by root over 2m m plus e, and then gamma naught. Okay. So you can do what? You can insert gamma naught square here, which is identity. Okay. And then club this gamma naught with dagger here to make it bar. So you write u bar alpha m0, then one gamma naught left, k slash plus m, gamma naught, whole thing divided by 2m m plus e. Okay. So now let me erase. So here, suppose I want to calculate gamma naught k slash gamma naught. Gamma naught dagger, k slash dagger, I think. K slash dagger. Okay. So you have here these things, gamma naught, gamma mu dagger, k mu, that is the k slash dagger, gamma naught. But gamma mu dagger was gamma naught, gamma mu, gamma naught. That's the identity I have shown you earlier, right? For just gamma mu dagger. And then you have gamma naught here again, and k mu I am writing in the last. So these will give you identity here, and again identity here. So you'll be left with gamma mu k mu, which will be k slash. So gamma naught k slash dagger gamma naught is equal to k slash itself. Because this is identity, this is identity. Okay. K mu is just number, no? 4 component vectors, just numbers. They are not matrices. Okay. So here this job is done. So this thing will be u bar alpha m0 k slash plus m divided by root 2m m plus e. Okay. So this will be your expression for the bar thing. You can
Sir?
do like, yes.
So when we have the Wigner little group representation, then we can go from massive case to massless case by just taking m goes to 0 limit or boosting a frame.
No. That is not very simple. The Wigner little group for massive case is just SO3.
Yeah.
And for that case is actually the what is called the Euclidean group, two
Yeah.
translation and this thing. Then you have to invoke what is called Wigner-Inono group contraction.
Yes.
From going from SO3 to, so it is not just simply taking massive mass going to zero limit case. You have to take, there are other parameters. So SO3 acts on sphere. So you have to take the radius, which will give you the length scale, and then take some proper ratio. Means you have seen when there are a couple of parameters involved, then you have to take limit in such a manner that something is held fixed and one thing increases, another thing decreases, product is held fixed. This kind of tricks will be necessary in taking the limit.
Yes,
Okay.
but we can go from the massive case to massless case. I mean, by some
Yeah,
tricks or something.
yeah.
But my question is, in that case, you have W dagger that remains keeps the P invariant, right? I mean, the momentum remains invariant under the Wigner little group representation.
Yeah. Momentum remains.
So
Yeah, for
yeah,
massive
so
case.
but here I can see that you have written gamma 0 K dagger, K cut dagger, and gamma 0, so it giving K. I mean, it's not keeping it invariant. So is it the reason that we cannot go from the massless or massive case?
No. What remains invariant?
Your K dagger doesn't remain invariant under gamma 0.
The K dagger, no, gamma 0 is nothing like your any Lorentz transformation or any, you cannot identify the group,
Yeah, yeah.
contraction. Gamma 0 is just a matrix. So why are you bringing that topic here?
In that case, we have some WPW dagger. So in here also you can see that some gamma 0 K dagger gamma 0. So
No. I don't see any relation between that case and this case here. Okay. It is just a simple identity here.
okay.
Okay. So likewise, you can prove uh, homework I am giving. Okay. So you can prove V alpha K, that is negative energy spinors, will be minus K slash plus M divided by 2M M plus E. Okay. V alpha M0. V alpha M0, this by itself, I write it is a top two components in the rest frame is 0 and the lower two components will be delta alpha 1, delta alpha 2. And this I write as 0 and chi alpha M0. Okay. So these two will go to this 0 and these two will go to this chi. Just for this. And once you just calculate in the similar manner, you will get sigma dot K divided by 2M M plus E, okay, chi alpha M0 E plus M by 2M chi alpha. Okay, that you please verify homework. Okay, and regarding the bar thing also, you will get ultimately V bar alpha M0 get this. Okay. It's a straightforward calculation the way I did earlier. So another homework for you now. This is straightforward to check because you have all the spinners and their kind of bars in the arbitrary frame, and you can easily verify that u bar alpha k u beta k. You see, this is is equal to minus v bar alpha k v alpha k v beta k is equal to delta alpha beta. There is a minus sign here. Okay, that comes from actually we defined v to be with a relative minus sign, not relative means with a minus sign here in front. Okay, so you'll get this. These are Lorentz invariant condition, and regarding these are just between u and vv, and if you take u bar alpha k g beta k, if you take a mixture of these things, then you get this is equal to v bar alpha k u beta k. This is 0. Okay. We just substituted it trivially, it will come out to be 0 in one line. Okay. So this actually prepares us to define what are called projectors. There are two means what I want to do now means these I've written down what are the various spinners for positive energies and negative energies. There are two kinds of positive energy spinners you get, two kinds of negative energy states. So you may ask what are the difference between different components in the same positive energy states? What are the different physical contents of these things? So I want to isolate the physical contents of these things. That I will be doing eventually. But before that, we would like to introduce what are the projectors in different positive and negative energy eigenstates. A projector, you know, means so okay. So just before I proceed, the concept of projector you have already seen in quantum mechanics or in linear algebra when you study. The idea is that if you have a vector space, say, okay, say x and y, 2 dimension. If you have a vector like this, I can project it to its component in the x direction. Project it means if this is the vector v, this will be the vector which will be PV. Projector, when it acts, it projects along the axis direction. So what it does, basically V, you write it as V I hat plus V1 I hat V2 J hat. The projector V will give you V1 I hat only. That means the projector acting on J hat will give you 0. So it kills something. This Y component it just kills off. So means everything, every time we see the projector, it projects out something. Means it annihilates some part of the component. In our life also, we project many things out. Okay, means we are not interested in something. We just ignore all this. So here also we are ignoring one component and retaining something of our interest. Okay, so this is one way of doing it. Another way of doing it is to say that I'll write the basic vectors in this way. Instead of I hat, I'll write these as 1, 0, and J hat is 0, 1. Okay, so V will become V1, V2. Isn't it? So if projection has to ensure that PV becomes V1 this thing, then what will happen? In this case, the projector I can write is the component of the vector in the direction which I want to retain. Right? So I can write V dot I, this is the component I want to retain. P acting on V. And the J part I am not writing. The original V was, I can write these as both ways. I can write V dot I hat. This will give me V1 I hat plus V2 will be V dot J hat, J hat. Okay. And V dot I, V is this thing, and I am defining like this. So how do I get V1? I have to take a transpose if I'm dealing with real matrices. If it is a complex matrices, then I have to take a Hermitian quantity. So V dot I hat, I can write V as a matrix this way, this transpose, and I hat is 1, 0. And then followed by, or this will give me the V1 and this will be give me 1, 0 again. ঠিক আছে না? হ্যাঁ বুঝলাম না ও ব্রেক হ্যাঁ হ্যাঁ শিওর 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 5 মিনিট ওকে আই এম টেকিং 5 minutes break. Now, if you take transpose, this is the matrix I'm associating with this. So you can write this as row matrix now. V1, V2, and 1, 0, 1, 0. So this will give you V1, 1, 0. That's what you want. হ্যাঁ 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 actually a better way of writing it actually will be this better way. Let me write it this way. This one I'll make I transpose I transpose V. That's the best way to write it. Is that it? I transpose will make you I transpose will make you row matrix. V will be a column matrix. So what we will get means that after projection PV. Okay, let others come then. 5 minutes.
আপনি বলেছিলেন না লাইকওয়াইজ ফর ভি কেস, ইউ কেসের জন্য আমার U3 আর U4 টা 0 হয়েছে, সেজন্য U1 আর U2 পেয়েছে।
হ্যাঁ হ্যাঁ
লাইকওয়াইজ ফর ভি কেস, সেক্ষেত্রে V3 আর V4 টা তো এক্সিস্ট করবে,
V3 V4 এক্সিস্ট করবে।
V3 টাকে আপনি V1 লিখেছেন।
হ্যাঁ হ্যাঁ মানে V3 বলছি না, নেগেটিভ এনার্জির জন্য ইউ মানে তুমি যেভাবেই নোটেশন দিতে চাও, মানে টপ টু কম্পোনেন্ট 0 হবে।
তো মানে টপ টু মানে ওটা নিচ থেকে ধরছিল।
হ্যাঁ নিচ থেকে ধরছি, V1 V2।
স্যার স্যার বলছি ওই ভি কেস যেটা বললেন ওই ক্ষেত্রে তো স্যার যেটা V1 M0 আর V2 M0 ওটা 0001 আর 0010 হবে, তাই তো? মানে লাস্ট দুটো কম্পোনেন্ট নন জিরো হবে।
বুঝলাম না, আবার বলো, আবার বলো।
না স্যার আমি বলছি স্যার ওই যে উইদাউট লস অফ জেনারেলিটি যেটা ইউ লিখেছেন সেখানে তো দুটো কম্পোনেন্ট পেয়েছি, এবার যখন ভি লিখছি তখন
ভলিউম অনেক কমে গেছে, ভলিউম অনেক কমে গেছে, কথা বোঝা যাচ্ছে না। আমি জানি না কেন তোমাদের অনলাইনে কথা ভালো বুঝতে পারি না। আবার বলো, তুমি একটু আস্তে আস্তে বলো, বলো।
হ্যাঁ স্যার এবার শোনা যাচ্ছে?
খুব আস্তে হয়ে গেছে, বলো। আচ্ছা তোমরা কেউ শুনে বুঝতে পারবে কি বলছে? হ্যাঁ আচ্ছা, ভির জন্য যখন করবে টপ রেস্ট্রিমের টপ টু কম্পোনেন্টস 0 হয়ে যাবে। হ্যাঁ আর বটম টু কম্পোনেন্ট সার্ভাইভ করবে। একটাতে 1 মানে বটম যদি দেখো মানে থার্ড এন্ট্রিটা উপর থেকে কাউন্ট করলে একটাতে 1
আর ফোর্থ
আরেকটাতে লাস্ট বটমটা একদম 1 হবে, আর বাকি সব 0 হবে। ওটাকে আমি V1 আর একটাতে V2 বলছি।
আচ্ছা স্যার ঠিক আছে। হ্যাঁ
তুমি বুঝতে পারছো তো আমি কি ফার্স্ট যাচ্ছি? দেখো মানে জিনিসগুলো কিন্তু ফিল্ড থিওরি ইজ এ ডিফিকাল্ট কোর্স। হ্যাঁ এটা আবার আমি একটু ফিল্ড থিওরি থেকে ব্যাক করে গেছি, কারণ এগুলো জিনিস তোমাদের মানে আগে পড়িয়ে দেওয়া উচিত ছিল। এই জন্য আমি কয়েকটা টপিক স্কিপ করে এসেনশিয়ালি করে আবার ফিল্ড থিওরিতে আসবো, ডিরাক ইকুয়েশনটা করে দিয়ে। আর পার্থ বোধহয় পড়াচ্ছে, ও ডিরাক ইকুয়েশন কিছু তোমাদের অলরেডি বলেওছে, তো কয়েকটা টপিক ওই করাবে আর কি। হ্যাঁ আমি ওগুলো স্কিপ করবো, কারণ ওটা ফিল্ড থিওরির মধ্যে ঠিক পড়ে না, ওটা অ্যাটমিক মলিকুলার ফিজিক্সেই পড়ে। হ্যাঁ মানে কে পড়ায় তার উপর ডিপেন্ড করে। ফিল্ড থিওরি হচ্ছে মোস্ট বেসিক সাবজেক্ট। জানে সে ওই রকম ভাবে পড়াবে, আর যে জানে না সে একটু মানে ওর কাছে অস্ত্র বেশি আছে বলতে পারো। হ্যাঁ ওটা জাস্ট একটা মানে বলে রেখেছি, দোজ হু আর ইন্টারেস্টেড ক্যান থিঙ্ক ওভার ইট। মানে এটা তোমাদের যারা ইন্টারেস্টেড নয় ওদের না মাথা ঘামালেও হবে আর কি। ক্লিফোর্ড অ্যালজেব্রার সঙ্গে ওই যে এক্সটেরিয়র অ্যালজেব্রার যেটা লিংক, এটা ডাইমেনশন, এটা তো এটা হচ্ছে 4 ডাইমেনশন ভেক্টর স্পেস না। এটা দেখো 6টা ডাইমেনশন, nc2 dx mu dx nu dx0 dx1, কারণ অ্যান্টিসিমেট্রিক তো dx0 dx0 সার্ভাইভ করবে না, তোমাকে আলাদা আলাদা নিতে হবে। আর যদি ইন্টারচেঞ্জ করো মাইনাস সাইন আসবে, তো তোমাকে nc2 মানে 4c2 মানে এটা 6 ডাইমেনশন হয়ে যাবে। এরকম এটা nc3 মানে 4c3 মানে 4c1 হয়ে যাবে, মানে আবার 4 হয়ে যাবে।
এটা আলাদা ভাবে
মানে হ্যাঁ, কিন্তু কেন মিউনিগুলি সার্ভাইভ করতে হয় সবগুলোকে ডিস্টিংক্ট হতে হবে না। তাহলে 0 1 2 3 ছাড়া বা তাদের উল্টো অন্য কোনো অর্ডারিং এ হবে, প্লাস অর মাইনাস অফ দিস, তার আর উপায় নেই। এখানে হয়তো এটা আমি লিখতে পারবো না এরকম, কারণ এখানে হয়তো জিরোটা মিস গেছে, 3টে আছে dx1 ওএইচ dx2 ওএইচ dx3, কিন্তু এখানে সবাই থাকতে হবে, তাই না? না এটা ডিরাক অপারেটর। ডিরাক অপারেটর তুমি যদি ভাবে গামা মিউজ গুলো তো একই এরকম ইয়ে করে, এটাকে ভাবতে পারো এটা ইট ইজ অলসো সাম সর্ট অফ ওয়ান ফর্ম, বাট ক্লিফোর্ড ভ্যালুড ওয়ান ফর্ম। ডিএক্স মিউর জায়গায় গামা মিউ আছে। ওকে, সবাই এসে গেছে? Okay, so I can write it like this. Okay, means the original vector I can write it in fact like this. I had then I had transpose V vector plus J hat transpose V vector, something like this. So I can, it is true for any vector in 2-dimensional case. So if I just remove the V now, I can write this is equal to identity I times I transpose plus J times J transpose. Okay, so this is gives you my completeness relation, 2-dimensional space. And if this is a column matrix 1 0, this is a row matrix. If this is a column matrix 0 1, this is a row matrix 0 1. In quantum mechanics, this column matrix is denoted by cat. Let me call it cat 1. The row matrix will be denoted by bra 1. And this will be cat 2, bra 2. So this will give you the completeness relation. Okay. So if you want to project to this thing, you take a subspace of that. That will give you the projection operator. That's how you get the completeness relation in quantum mechanics. This is just to remind you, you know all these things. But so here also, what is important is that you have to have some sort of column matrix followed by a row matrix. So here also I do the same thing. I define my projection to energy eigenstates as this thing. lambda plus k by definition is equal to sum over alpha equal to 1 to 2 u alpha by definition u bar alpha k. So you see, this is a column matrix and the bars are a row matrix. Dagger multiplied by gamma naught. But dagger itself becomes a row matrix multiplied by 4 by 4 gamma naught. It will give another row matrix. Okay. So it will be column matrix followed by this thing. So this will be my projector to positive energy eigenstates. Alpha equal to 1 and 2. Okay. Remember, in the rest frame also they are positive energy, and in any other frame it will persist to be positive energy. You cannot make a Lorentz transformation and go from positive energy states to negative energy states. Okay. Nah, because you see, with energy momentum, suppose I am drawing one spatial dimension, E, suppose P1, because the momentum in the x direction. What do you have? Relation is E square minus P1 square is equal to m square. So what happens is that you have a 45-degree line here, and you have the so-called the mass shell. This is satisfied by this. There are two mass shells. These are hyperbola. The moment the particle mass is fixed, energy and momentum cannot take arbitrary values. In space-time, for example, if you draw, it can be any points, events. But in the momentum, energy momentum space, the four momentum of the particle, if they are positive energy, they has to lie down in this so-called mass shell. There is no way out. Here I have suppressed 1 and 2 because I cannot draw. At most I can draw another P2 axis, which will be obtained by surface of revolution around this axis. But if you want to all three, then I cannot draw. I cannot imagine. Okay. So that's why it is convenient to suppress one of them at least and retain much. Best to see it this way. Negative energy states will correspond to this kind of four vectors. Okay. So no Lorentz transformation will take you from here to here along this mass shell. Okay. But here to here, again, if you have a negative energy particle, then you can go by Lorentz transformation along this mass shell, but you cannot jump from here to here. Okay. This is not possible. So I'm here restricting myself to positive energy solution. As I told, alpha equal to 1 and 2 correspond to positive energy solutions in the rest frame. So it will persist to be positive energy solution, maybe with different energy. Because here also you see, if you make a Lorentz transformation, you go to here. So energy will be different. For the rest frame, this will correspond to the rest frame, this point. Energy will be exactly equal to mass. So this point has mass, m. All other points will have higher energy above the mass. Gamma m, remember, gamma will be more than 1 energy. So you are defining this kind of projection operator. Okay. And now it is a matter of you, I have given all the expression u alpha dagger. So what you can do, you can just substitute. I am just writing few lines here. Alpha equal to 1, 2, k slash plus m. Okay, and just substitute the expression I have derived. So now what I have to do, I have to first calculate what is this object in the rest frame. The rest frame, it was just calculate delta alpha 1, delta alpha 2, 0, 0. Delta alpha 1, delta alpha 2, 0, 0, and followed by 1, 1, minus 1 along the diagonal. So this is the U dagger row matrix, and gamma 0 is this thing. Okay. So now if you multiply, what will you get? You get U alpha টা এটা M0, U dagger টা এইটা, এখানে তো dagger gamma naught আর gamma naught টাই। So this will be delta alpha 1, delta alpha 2, sorry, delta alpha 2, no, sorry, this will be delta alpha 1 itself, delta alpha 1. So you see, now delta alpha 1 will be this term. This term will be delta alpha 1, delta alpha 2, right? But you are summing over alpha equal to 1 to 2. It is not possible to have alpha values simultaneously 1 and 2. So it will be 0. So this will be 0. Right? Similarly, this will be also 0. And this will be delta alpha 2, delta alpha 2. Rest of the components will be 0. Okay. But again, when you sum over alpha equal to 1 to 2, this part remains constant. So when alpha equal to 1, only this part will survive, 1, and this will be 0. And alpha equal to 2, this will be 0, and this will be. So when you add them, because the rest of the thing is held fixed, there is no alpha dependence. When you add them, you will get 1, 1 here. Is that it? So you will get, when you sum over alpha, so sum over, if you carry out the summation over alpha, you will get 1, 1 here. 1, 1, 0, 0. Okay. And then if you multiply with this thing, this is also identity. Because so this part is identity, so it will remain like this ultimately, even if you multiply. Because this identity into identity will give you identity. Identity into 0 will give you 0. And this part will, so this part will have no contribution in the final product. So this I can write down from the entire thing. This is simple matrix multiplication. And what is this thing? k slash plus m These I can write down as 1 plus gamma naught by 2. And this will be again k slash plus m by another factor of root 2n and plus e. Okay. So ultimately this will be 1 by 2m m plus e, and you have k slash plus m 1 plus gamma naught k slash plus m. Okay, this is your lambda plus k. Okay, now this term is trivial. So let me calculate k slash plus m gamma naught k slash plus m, just to show you some of the manipulations involving gamma matrices. আরেকটা হ্যাঁ একটা রাইট রাইট ধরো তো ভুল করলাম নাকি রাইট একটা 2 থাকবে Okay, so let me k slash plus m gamma naught into k slash plus m. এটা ক্যালকুলেট করি k slash plus m gamma naught k slash plus m. Okay. So this will be k slash gamma naught plus m gamma naught k slash plus m equal to k slash gamma naught k slash plus m k slash gamma naught plus m gamma naught k slash plus m square gamma naught. Okay. কি দাঁড়ালো k mu gamma mu gamma naught gamma nu. K mu k slash k nu gamma nu is another k slash and gamma naught is sandwiched between them. This k mu's I have brought them forward. These are simple numbers. Okay, and here I have anti-commutator between k slash and gamma naught. Right? K slash gamma naught plus gamma naught k slash is the second and third term, and this is your m square gamma naught. Okay, so now I calculate this k mu gamma mu gamma 0. So I can write this as gamma mu gamma 0 anti-commutator minus gamma 0 gamma mu. Okay, gamma nu plus m k mu gamma 0 plus m square gamma naught. Okay, so this will be k nu. This is 2 eta mu 0. 2 mu Clifford algebra, that's it. 2 eta mu 0 minus k nu gamma 0 gamma mu whole thing multiplied by gamma nu. And this thing 2m k mu eta mu 0, anti-commutation relation, and this is nothing but m square gamma naught. Okay, so this term becomes only mu equal to 0 will survive. So k0 e, in the rest frame it will be n. In general e. So this part will be just e, 2me. And this part again mu 0, so this will become 2e k nu gamma nu, so it will be k slash. Okay, and just a minute, how the manipulation goes. I've taken a bit longer route. Maybe let me do it this way. Just let me redo it. Okay, this is just let me redo it. All right. I can write it like this. K mu gamma 0 plus m gamma 0 k slash plus m, and this I can write down as k mu 2 eta mu 0 minus gamma 0 gamma mu plus m gamma naught k slash plus m. And this I can write down as 2e minus gamma 0 k slash plus m gamma naught k slash plus m. Okay. Gamma mu gamma 0 I have written as anti-commutator and minus gamma 0 gamma mu, and the anti-commutator is twice eta mu 0 minus this thing, and plus m gamma naught is as usual. So this becomes eta mu 0, so mu equal to 0 will survive, so k0 will become e, so 2e minus gamma 0, k mu I can take inside, k mu gamma mu contracted gives k slash. Okay, plus m gamma naught. Huh? Now I can write this as 2e k slash plus m 2e k slash plus m minus gamma naught k slash minus m. These two terms I can write down, I can take gamma naught common, gamma naught minus gamma naught k slash, and this will be m gamma naught, is minus common, so it is k slash minus m. Okay? So it will be k slash plus m. This will go to 0, so it will be 2e k slash plus m. Okay. So what is delta plus then? Delta plus means I have simplified, so I make use of this thing, k slash plus m gamma naught k slash plus m is 2e this thing. So I have 1 by 4m m plus e here, and here I have k slash plus m whole square plus k slash plus m gamma naught k slash plus m. And then I have 1 by 4 m plus e, and here I can take this thing identity, so I have k slash plus m whole square plus 2e k slash plus m. Okay. So 2e,
স্যার
huh,
স্যার বলছি ওই ক্যালকুলেশনটা যেটা করলেন কে স্ল্যাশ প্লাস এম গামা জিরো কে স্ল্যাশ প্লাস এম, ওর লাস্টের লাইনটা একবার বলবেন কি করলেন?
এইটা
হ্যাঁ
এইটা
হ্যাঁ 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 হ্যাঁ
তো এটা তো মানে আমি ইয়ে করলাম, এটা এতটুকু পর্যন্ত ঠিক আছে।
হ্যাঁ স্যার।
আচ্ছা, তাহলে আমি এখন এখানে 2e কমন নিলাম, হ্যাঁ 2e কমন মানে 2e ইন্টু k স্ল্যাশ প্লাস m করলাম, আর এইখান থেকে আমি গামা নট কমন নিলাম, মাইনাস গামা নট কমন নিলাম, তো পড়ে থাকলো k স্ল্যাশ মাইনাস m, তারপর আবার k স্ল্যাশ প্লাস m দিয়ে মাল্টিপ্লাই হলো, তো k স্ল্যাশ মাইনাস m ইন্টু k স্ল্যাশ প্লাস m টু 0।
আচ্ছা আচ্ছা হ্যাঁ ওটা জিরো, হ্যাঁ ঠিক আছে।
ঠিক আছে, তো এতটুকু হলো। এখন এটাকে সিম্পলিফাই করতে হবে, 1 by 4m m plus e k slash square, which will be k square, it will be m square, 2m k slash plus m square, আবার m square আসবে, k slash square m square দেবে, আবার m square দেবে, 2m square plus 2e k slash plus m। তাহলে কি দাঁড়ালো, আমি এখানটায় করি, this is equal to 1 by 4m m plus e, এখান থেকে 2m কমন নেই, k স্ল্যাশ প্লাস m, প্রথম দুটো টার্ম থেকে I take 2m common, k slash plus m, then I have plus 2e k slash,
স্যার প্রথম আর লাস্ট টার্মটা কমন নিলে ভালো হতো।
হ্যাঁ হ্যাঁ
ঠিক আছে ঠিক আছে, ওকে।
okay, so I have this thing, 2 cancels, 2 here cancels, then 2, so 1 by 2m m plus e, and here I have taken k plus m common, so I have e plus m, k slash plus m. So e plus m cancels. I have got finally k slash plus m by 2m. So this is my lambda plus k. This is an important result. Okay. Okay. So likewise, again, I leave homework exactly the same thing. Define lambda minus k. Part of the definition. This starts with a minus sign. Alpha equal to 1 to 2. V bar alpha k. V alpha k. Okay. কি বুঝলাম না বার ও কলম রাইট ইউ আর কারেক্ট তো এটাকে যদি করা যায় 2m you get minus k slash plus m. Do it the same way, same line of manipulations. And verify the following relations. Again, homework. Kala, you are noting them down, right? Verify. Number trace of two আর থার্ড হচ্ছে lambda plus k plus lambda minus k is equal to that's what I want actually. The project into positive eigenstate, energy eigenstates, and then projects to negative energy. Total, that should give rise to identity operator. Trace. No. Argument এর ভিতরে k থাকে. This argument is k. This simple you can read off answers. No, lambda plus k, lambda two dimensional, no? देखो, this is a 4x4 matrix, na? Total 4-dimensional space. So space should be 4, and they should be equally distributed when the positive and negative eigens. Think that way. 2. Okay. So shall I stop here? Then After lunch, I'll talk about little bit of this projection and then project it into spin states. Okay, and helicity I will describe. If time permits, I'll talk about the wave packets. Let's see. And probably any question from the onliners? Hello? Sanmojit?
হ্যাঁ স্যার,
No question.
হ্যাঁ স্যার বলছি ওই ভেরিফাইড 2 নম্বর যেটা বললেন ওটা একবার বলবেন কি লিখেছেন?
Derivative trace. Trace টা lambda plus minus k is equal to 2.
স্যার ল্যামডা প্লাস মাইনাস টেকটা কিভাবে মানে করা
এই
হচ্ছে?
যে ডিরাইভ করলাম এখন lambda plus minus k, k slash plus m by 2m.
হ্যাঁ ওটা তো ল্যামডা প্লাস করলাম আর ল্যামডা মাইনাস করলাম, আর ল্যামডা প্লাস মাইনাস, ও আচ্ছা আচ্ছা বুঝতে পেরেছি। স্যার ওটা ট্রেসটা স্যার 4 হবে না?
হ্যাঁ?
ওটা স্যার ট্রেসটা 4 হবে না?
না 4 হবে না। ও কি করে হবে? করে দেখো। k slash plus m আরেকটা তো হচ্ছে minus k slash plus m by 2m. m টাইমস কিন্তু আইডেন্টিটি অপারেটর, ওখানে আইডেন্টিটি 4 ডাইমেনশনাল আইডেন্টিটি।
হুম
ওখানে ট্রেস দিলে মাইনাস k স্ল্যাশ তো কেটে যাবে, খালি m থাকবে। m by 2m মানে হাফ, হাফ ইন্টু আইডেন্টি 4 ট্রেস নিয়ে যেটা হবে, দ্যাট উইল গিভ ইউ 2। মানে এটা জাস্ট মুখে মুখেই করতে পারছি।
আচ্ছা আচ্ছা হ্যাঁ স্যার।
ঠিক আছে, আমরা আবার 2:30টার সময় মিট করব। ওকে। Okay, so let me start with the probability density. Okay, so probability density, I have derived the form of the current earlier, psi bar gamma mu psi. So zeroth component, there's a time component of this thing will give you the probability density. So let me write rho by definition is identified with J0 of k now. This is the psi bar gamma 0 psi, right? Now this thing is, I have taken psi to be, psi of x to be e to the power say minus I k dot x u k. So let me substitute here, they are function of x. Okay. So psi, so it will be psi dagger x. Okay, gamma naught and
স্যার
gamma
একটু
naught.
বড় করে লিখলে ভালো হতো।
Huh? Acha. So in the bar there is a gamma naught here, there is gamma naught here, they will give you identity. So psi dagger x, psi x. So this, if you just substitute, the phases will disappear. You will get u dagger k uk, right? That's what you will get. Okay. But instead of calculating using the bar here, what I'll do, I'll start with the calculation, means I'll go one step back and write in terms of u bar itself. u bar k gamma naught uk. Okay, just write it like this. Now I write it as 1 by 2 u bar k m 2 gamma naught uk plus u bar k 2m gamma naught uk. Okay, you see I have this is a 2m I have inserted, so I have divided by 2m here. No, not 2m, this is just m I have, this is 2m. I have two terms here like this, same term. Once I have written m in front of gamma naught, another times m here. Okay, same kind of thing. Okay. Now you know that k slash minus m uk is 0. To take dagger of this thing and then multiply by u bar k slash minus m also will be 0. The conjugate form of these things is this. That you can easily verify. You just take dagger and then insert gamma naught suitably, you get this. Do you want me to do it, or you will be happy to take it as a homework? Huh? Kala?
It's okay.
Okay, right? So 1 by 2m. So I can write m u bar k as k slash u bar k. So I can write u bar k slash gamma naught uk, and here I write u bar k gamma naught m uk as k slash uk. Okay, so I have 1 by 2m u bar k anti-commutator of k slash gamma naught, because it is k slash gamma naught plus gamma naught k slash, and u bar k is in the left, uk in the right. Is that it? You just split k slash gamma naught, and second term will be gamma naught k slash. But as I told you from the Clifford algebra, basic Clifford algebra, gamma naught will anti-commute only with the gamma naught. Means gamma naught means it is non-vanishing anti-commutator. Gamma naught will be twice this thing. Gamma I will be 0 anti-commutator. So only the time component of k slash will survive here. The time component of k slash will be E gamma naught. Right? E gamma naught and gamma naught. And this is nothing but twice, 2 times identity. Right? Twice eta 0 0. So this is equal to 2e. So this being a number, I can bring it out. These two will cancel, and I'll be left with E by m u bar k uk. Right? Okay. If I were to do it some alpha, so you see means this is for general psi bar, this thing if you do. If you compute component wise separately, suppose if you were to calculate it component wise separately like this, psi bar the plus component of these things, alpha th component, gamma 0, psi plus, because I have taken the positive energy solution, so I am writing this way, the beta. Any question? Okay, so it will be E by M delta alpha beta. Okay. So this E by M, this E by M is the Lorentz contraction factor. That means the probability density also will not remain invariant under Lorentz boost. It should change by this E by M factor, so that the total probability within say x and x plus dx, total probability, this into dx, this is the probability density, into dx will give the probability between x and x plus dx. That will remain invariant. The length contraction will compensate this factor. It will be opposite of this. Okay. What I am saying is that this is precisely your gamma. Gamma, this E equal to gamma n. Remember, this factor 1 by gamma comes in your length contraction. So it will cancel. Now here I have, you can do the same thing with the E plus minus, for minus also it will be the same thing, same results you will get, verify. Okay. You may ask what happens if I mix them, 1 plus 1 minus. In this case, what will happen is that psi bar plus minus alpha gamma naught psi beta minus plus. I want to calculate this. Okay. For two states, for psi say alpha x plus is equal to e to the power minus I k dot x, and which I write is equal to minus I e t minus k dot x. Is the k0 is e. Energy. Okay. Time component up or down doesn't matter. Let me emphasize it again. So this k vector is the ki. Is the, alpha plus with positive energy eigenvalue. Yeah, uk, right. U alpha k. Sorry, U alpha k. Okay. Now you consider for the negative thing.
স্যার বলছি প্রথমে যেটা লিখেছেন e to the power minus I k x, ওখানে k টা 4 ভেক্টর তো?
It is 4 vector. The moment I write is the 4 vector.
Okay.
The 3 vector, I'll put a vector mark overhead. Psi beta minus x, this I'll take negative energy eigenvalues, but the same 3 momentum. Okay. So let me write it as A I k tilde dot x. Okay. V beta k. Okay. K tilde. Where k tilde is equal to, means the same 3 momentum, but it will be minus E k vector. 3 vector is same. 3 momentum, so energy is opposite. So you are considering these 2 mass shells I drew earlier. One up, another down. But the 3 momentum vector is same. Okay. So to draw it again, so you are considering one vector like this k, another vector like this k. This is k tilde. They have opposite energy eigenvalues, but the same spatial component. Okay, k and tilde. So if you can calculate this, you can show this again. I'll leave as an exercise. I'll show that this will vanish. Oh, this is simple. You follow? Okay. So now, having discussed this projector into energy eigenstates, positive or negative. Now let me introduce another projector, which is projector into definite polarization states. I can erase all this, right? Okay, so recall this Pauli-Lubansky vector, which I had defined earlier. Pauli-Lubansky vector was W mu equal to minus half epsilon mu nu rho sigma p nu j rho sigma. Right? That was up to আমি আসছি বলছি Okay. Okay. Now introduce a space-like unit 4 vector and mu space-like. Okay. Huh? No, 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 no. Poincaré algebra to কোথায় commute করে? You see, P mu P mu they commute among themselves, but with J that complicated relation is actually given by semi-direct product of Poincaré group is a semi-direct product of the Lorentz group, homogeneous Lorentz group, the translational group. I discussed it in a revise your group theory class. Okay. So, so that n mu is equal to -1. You need space-like vector. You know this time-like vector or space-like vector or light-like vector, they are Lorentz invariant concepts. You know from special relativity, right? So, if you can, means you are allowed to go to a frame where the time component will entirely vanish. Only the space part will survive. Likewise, if it is a time-like vector, you can go to a frame where only the time component will survive. Space component will be entirely vanishing. But if you go to any other frame, all the components will survive, but the time component will exceed the space component. That's why it is a Lorentz invariant concept. So we want to make use of this freedom of choice as far as the reference frames are concerned. So what I am doing here, I contract W mu with this n mu. So I write W dot n is equal to W mu n mu. Okay. The moment I contract, I get a Lorentz scalar. So again, I'll proceed with some simplifications, and then eventually I will go evaluate it in the rest frame, where this thing n will be completely space-like. So only the special component will survive, and that too, say I will choose it as a unit vector in the z direction. No time component, no x component, no y component. Where is the space-like this thing? It will satisfy this. N mu equal to -1. So I'll go to that particular frame to evaluate it. But before that, you recall, J rho sigma consists of two terms. One is the orbital angular momentum, and the spin part. Orbital angular momentum contains this capital P. So the moment that I did last time also, you recall that. So the moment you have this, suppose you will have terms like P rho or P sigma. The moment you have P rho, P nu, that will be commuting, so it will be symmetric under interchange of nu and rho, right? But it is antisymmetric, so it will collapse. So the orbital part will vanish. All that you will be left with is actually the spin part. Okay, so I can safely write -12 epsilon mu nu rho sigma P nu. J rho sigma will be what sigma rho sigma by 2. Right?
স্যার অ্যাঙ্গুলার মোমেন্টামের জন্য কিভাবে জিরো হবে ওটা আরেকবার বলবেন?
Huh?
অ্যাঙ্গুলার মোমেন্টামের জন্য কিভাবে জিরো হবে?
It was the last time I told J rho sigma is equal to L rho sigma plus half sigma rho sigma. This is the spin part. And for L rho sigma, it is x rho p sigma minus x sigma p rho plus half sigma rho sigma. So the moment you have this thing contraction, I mean, so it's p nu. So you will have terms p nu p sigma. So it will be symmetric under interchange of nu and sigma, and it is under interchange of nu and sigma. It is antisymmetric. So it will collapse. So likewise this term also. So all that you are left with will be the spin part, and that I have actually calculated last time. The spin of the particle which satisfies the Dirac equation is half, right? I have proved it. So you are left with this, right? And and sigma mu sorry, it will be 2 here. This will be this thing, and sigma rho. So then that will have minus 1/4 already. Epsilon mu nu rho sigma. Oh, you have eta mu also, n mu, p nu, and sigma rho sigma. They will get another. Sigma rho sigma was commutator of, what are the p factors? Sigma p factor was I by 2 or something. I by 2. I by 2.
Gamma rho with gamma sigma.
Gamma rho gamma sigma. Right? Is it okay? So now I have to calculate this. Now to calculate this, I gamma rho gamma sigma. So I have minus I by 8 epsilon mu nu rho sigma and mu p nu gamma rho gamma sigma. Let me write and interchange the second term. I interchange rho and sigma. That will generate, will kill the minus sign, and then it will be compensated from here. So I'll get back to I by 4. Is it okay? Now I go to the rest frame, because this is a scalar, right? So I can go to the rest frame and to evaluate it. Means I can write just W dot N is equal to this thing, because value is independent of the frames where I calculate it, as I told you earlier. Rest frame. So here rest frame I choose where P0 will be the actually my K here. P is actually my K nu. So nu will be 0. And mu I choose only the third component. So n3 is equal to 1 and rest of the components are 0. Okay, it obviously satisfies n mu equal to -1, right? Are you all following? Huh? And so 3 here, 0 here, and k 0 will be m. So here it will be minus I by 4 epsilon, mu will be 3, mu will be 0, 3, 0. So you are left with just 1 and 2. So I write 1, 2, gamma 1, gamma 2. Another term will get epsilon 3, 0, 2, 1, gamma 2, gamma 1. Okay? Huh? I can choose any frame. No? I am choosing means eta w dot n I have to calculate for some given space-like unit vector. Okay. So this unit vector I am choosing to be space-like. So I am going to the rest frame. I am choosing it to be given by entirely a spatial vector. That means no time component. Third component I chosen it to be along the direction of z-axis. So n3 equal to only 1. All other components will vanish. Time component as well as x and y components. So n0 will be 0, n1 will be 0, n2 will be 0. Only n3 equal to +1. No, I'll come to that. Means here I am considering, just go through the steps. See whether you have any objection to any of the steps. The thing is that w dot n, the moment I consider any space-like forward vector whose norm is -1, space-like has to be -1, right? It is a Lorentz invariant quantity. So I calculate in the rest frame. In the rest frame, I choose the n to be such that it is oriented in the z direction. Okay. So then I get this. Now I defined epsilons for you earlier. Epsilons, the convention I have used. This thing is equal to minus I by 4 epsilon. If I raise all of them, it will cost you minus sign, right? Epsilon 0, 3, 0, 1, 2, gamma 1, gamma 2, and again it will cost you minus sign. Epsilon 3, 0, 2, 1, gamma 2, gamma 1. Okay. So here 0, 1, 2, 3, I had taken it to be +1 by definition. Remember, stick to the convention. I am choosing. So here, from there to there, how do you go? 3 means 0, 1, 2, these are in the right order, but a 3 occurs here, so here 3 in the front. So you have to go past 1, 2, 3. Then you will go back here. But 3 permutations are required. So it will odd number of permutations. So it will pick up a -1. So it becomes +1. Minus I by 4 +1. Gamma 1, gamma 2. And here it is, you can again go here, it will be with this minus or this, just this thing, will be epsilon 0 to 1 3 with a minus sign, not this minus, just this thing up to this. Okay, and so again 1 and 2, so it will be plus epsilon 0 1 2 3. So this will be plus 1. So this will be minus 1, right? Gamma 2, gamma 3, gamma 2, gamma 1, right? Okay. So gamma 2, gamma. So now what is this? Minus I by 4. Gamma 1 is what? Gamma 1,
half sigma 1.
0 sigma 1, 0 sigma 1 minus sigma 1, 0, minus sigma 1, 0. Gamma 2 is 0 sigma 2 minus sigma 2, 0, minus zero sigma 2 minus sigma 2, 0, and 0 sigma 1 minus sigma 1, 0. So now I'm done with the matrix multiplication. You can do easily. I will not do this. You will get this is equal to total thing will come out to be. Actually, I missed some term. I have written only these things. Mass term I have missed. K0 will have mass m, I am mass factor. Okay. So ultimately, if you do it carefully, you will find that it is given by this. So commutator sigma 3 kind of stuff will come, and ultimately you will get anyway. So m by 2, sigma 3, sigma 3, sigma 3, sigma 3, 0, 0. Something like this. You check, I may be making some mistake, plus or minus. Okay. This you can easily check. On the other hand, you see, you can calculate this stuff. Let me calculate this object. Gamma 5 n slash k slash. You calculate this. So it's the same n. Expand to the rest frame. This is also a scalar. Actually, this is pseudo scalar because gamma 5 occurs, but don't bother. You can go to any frame of your choice to calculate it. Okay, just don't change the orientation of the frame, left-handed or right-handed or right-handed. So you make an SO3 or SO1, 3 transformation, L plus up arrow, proper orthogonal group. As long as you are in that subgroup which is connected to the identity, this is invariant. Okay, so you can evaluate it with the rest frame. You can show that this also you will get the same result. So you show this homework, gamma 5 n slash k slash. So what happens is that is minus half, minus half. So ultimately, so if they match, you see both of them are Lorentz invariant quantities, these as well as this. And if they match in one frame, they should match in all other frames. Is that it? So I get the equality W dot n is equal to this. Okay. This is very important relation. So anyway, W dot n is this. So I can get W dot n by m is equal to half sigma 3 in the block diagonal. I call it half capital sigma by definition. But sigma is sigma 3, or sigma vector is sigma. Okay. So with this choice, now you can see that W dot n you have calculated. It is given by this. So you can make it act on this different polarization spinners. So W dot n by m is equal to acting on U1 m 0. So it is a rest frame. So I'll have to make it act on the spinners written in the rest frame. You will get equal to half U1 M0 U2. If you have W dot n by m U2 M0 is equal to minus half U2 M0. W dot n by m V1 M0 equal to half V1 M0. W dot n by E2 M0 equal to minus half E2. So what does it shows? So it shows that when you have rest frame, the U1, remember top component is 1, rest of them 0. They represent spin half particle, positive energy. This represents U2 represents spin minus half particle with positive energy. U's are positive energy. These are negative energy spin half particle. And this is negative energy spin minus 1 particle. So different, these 4 components have independent interpretations. Energy as well as the spin content. Okay? And this is with respect to our choice of n, which we have chosen in the rest frame to be given by a unit vector in the z direction. Okay? And that we can do without loss of any generality. So, is it okay so far? Okay. So these were written in the rest frame. I can just Lorentz boost it and write it in the arbitrary frame. Okay? Because these are Lorentz invariant quantities. W mu is the 4 vector, contracted with another 4 vector, give you Lorentz invariant quantities. So the matrix under which the U's and V's transform, I can apply that matrix, S matrix that I introduced, under which this transformation it undergoes through a representation of the Lorentz group. Okay, so I can just arrive at the corresponding relations in arbitrary frame. So in arbitrary frame, it will be given by this kind of relation. I can write down, you can check after a Lorentz transformation. W dot n by m minus u alpha k equal to 1 by 2m gamma 5 n slash k slash u alpha k. You see, sometimes I'm not very careful about the notation. Sometimes I'm writing a superscript enclosed in a bracket, or sometimes I'm writing as a subscript. You don't confuse, they're same. Okay. And this is equal to k slash when it acts on these things, it will give mass eigenvalue that m will cancel with it. Okay? Because this is the identity I have just proved. I'm making use of that. So the m will cancel. I'll have 1 by 2 gamma 5 n slash u alpha k. Okay? And plus minus. This depends upon alpha is equal to 1 or 2. No, this is plus minus half q alpha k. Okay. And another thing, minus w dot n by m v alpha k. If factor to chali do na, just if factor. V alpha k. Likewise, you can just write 1 by 2m gamma 5 n slash k slash v alpha k equal to minus half gamma 5 n slash v alpha k is equal to plus minus half v alpha. Okay. Again, I am making use of this thing. K slash v alpha is equal to minus m v alpha. Right? So that's why the minus m comes, and so this m cancels, and you are left with a minus sign. Okay? You just check this thing.
স্যার এটা মানে কি প্লাস ইউ1 মাইনাস ইউ1 দুটোই আসতে পারে?
না না না, যেটা বললাম আলফা ইকুয়াল টু 1 হলে প্লাস, আলফা ইকুয়াল টু 2 হলে মাইনাস। ওকে, হ্যাঁ হ্যাঁ, 2 লাইনের হোমওয়ার্ক মুখে মুখেই করতে পারো, তবুও করে দিচ্ছি, লিখে দিচ্ছি হোমওয়ার্ক। হ্যাঁ, so I can combine these things and see that gamma 5 n slash actually has, so I can just focus on this part. So what do you get? Let me erase this part. Gamma 5 n slash u alpha k is equal to plus minus mu alpha k. Okay, and gamma 5 n slash v alpha k equal to minus plus v alpha k. Okay, because there is a minus sign here, so it will become minus plus. So as far as gamma 5 n slash operator is concerned, the sign flips here for u and v. Okay, this suggests that we define the projection. We therefore define the projector Pn to half gamma 5 n slash. Okay. And just project it. And the projection operator should satisfy its squares to itself. You can check. If you take Pn square, it will be Pn itself. This is the project, because you remember the simple picture 2 dimension will give you. You can project by ignoring the y component. If you again do it, it will remain same. So projecting it once or twice or many times is same as doing it once. So p square must be equal to p. Huh? So what does it mean? P square is eigenvalue. If you write lambda square equal to lambda, so lambda will be either 1 or 0. So it has 0 eigenvalue. So projection operator is not invertible. And it is expected because there are many vectors which have the same x component. Y components are different. After projection of all of them will go to the same vector lying in the x-axis, right? So the complete information about the z component is lost because you have deleted it. Okay, so it is not invertible. So here also you find that projection operator satisfy, you square it, again take it as a homework, check for yourself that Pn square is equal to Pn. Okay, and
স্যার প্রজেকশন বলতে কি প্রজেকশন, মানে এই কনটেক্সটে প্রজেকশন বলতে কি বোঝাচ্ছে, কোন স্পিনারকে প্রজেক্ট করছে?
হ্যাঁ, এটা প্রজেক্ট করছে u1 কে, so you check again, take as a homework Pn acting on u1k equal to will be u1k Pn acting on v2k v2k will be v2k. Okay, and this is related to me. So u1 and v2 is isolated. It is because you see I have, okay, let me explain it very soon. So acting on u1, it will retain it u1. Acting on v2, it will give v2. If it acts on u2, it will give 0. Pn acting on u2 k will be 0. Same with p2 acting v1k, Pn acting v1k will be 0. So both this u2 and v1, they will collapse. So they will retain only the u1 and v2. হ্যাঁ, মানে আমি এক্সপ্লেন করছি এটা। second component, top or bottom. Okay, top or bottom ke project korche. So from this relation, I see that Pn plus Pn projects to U1k and V2k. Also, since I also, since P in our case N3, this I am designating for the particular choice of N I am doing, where it is oriented in a third direction with value 1, component 1. All other components are vanishing. So with this choice, I append a subscript here called 3. Okay. So this, if you just calculate, it is 1/2 identity plus gamma 5 and 3 slash. If you calculate, you will get half identity plus sigma 3, 0 identity minus sigma 3. Okay. Okay. You see here you automatically get minus sign. So what happens is, so this implies, you just check it. This is the same, again left as in homework. Simple algebraic manipulation, matrix multiplication. Okay. This implies that Pn projects into state which has spin value sigma dot n is equal to plus minus half for positive or negative energy solutions. Okay. So that explains the thing. If you calculate it explicitly, you will find there is a 1 plus sigma 3 occurs here, 1 minus sigma 3. You recall in non-relativistic case. Non-relativistic case, 1 plus sigma 3 by 2 is the spin projected in the spin up state. 1 minus sigma 3 is the spin projected for the lower state. But here I have calculated in the rest frame and also with this particular choice of choosing the third direction. Okay. So in this rest frame, this top, it will act on top two components. It will act on the bottom two components. Top two components are positive energy solutions. Lower two components are negative energy solutions. So in general, that will happen. It will project to plus or minus half states for positive energy. So for positive energy, it will project to spin half as determined by this space-like vector n. Okay, and will project to minus half spin state for negative energy solutions. Okay. Okay, so
সেই W ডট N বাই M এর কি ইন জেনারেল কোনো নাম আছে অপারেটরটার?
you can call it some sort of helicity operator, sort of, because it brings out the eigenvalues of this operator, gives the spin part. So you can actually use the spin part. Helicity is a more general name. It's generally used for massless particle, but here also you can say it like this. So I'll now actually introduce the concept of helicity very soon. So, so clear everything? So, in presence of this projection Pn, the eigenspinners of Pn are denoted as Pn Qn is for positive energy, and Pn Vkn equal to Vkn for negative energy. Okay. And they have the following properties. Again, I'll leave it homework, verify. The following properties. So the projector into the energy states commutes with the projector in the polarization states. Okay. So you can do in whatever order you like. First project to the energy states, and then project to the Pn. Suppose you project lambda plus, so you'll get the use. Then project Pn, you'll get the spin half. Okay. Or if you project to spin half, you will get top and bottom quantities. Then project the energy, it will automatically again that the positive energy thing will be chosen, selected automatically. So you can do any order. You can also check the corresponding matrices, the commute. Okay, that's expected. Okay, this is number one. Number two. Lambda plus k Pn plus lambda minus k Pn plus lambda plus k P minus n and lambda minus k P minus n. Okay. This will give you the complete resolution of the identity. Another way of writing. This is also expected result. Okay? P minus n. That means you flip the sign of the direction. N3 equal to plus 1 I had taken. Now you take N3 equal to minus 1. It will give you the opposite spin, right? So the thing is that the first term gives you, suppose n equal to N3 for simplicity. In the rest frame also. Lambda plus k will give you the U1, U2. Or you are first, anyway, order doesn't matter. Suppose you do the opposite order. Lambda plus k will give U1, U2. Pn3 will make you select the up component. Then lambda minus k will give you negative energy. Pn will also spin negative, spin down. Lambda plus k will allow you to, so again u, but with a spin down. That's a minus n. And that will give you, against negative energy, spin up. Right? Minus n will give you, so you are flipping the sign of this n in the spatial component. That's what I'm designating by minus n. It will also be another space-like vector, unit norm, but pointed along the minus z direction in the rest frame. And then for any other frame, it will be related by Lorentz transformation. Now, I'm talking about only proper orthogonal Lorentz transformation. No parity or time reversals being invoked at this stage. Okay. Okay, everything clear? And finally, we check this. Okay. Now I come to the helicity. In my group theory class, I had discussed helicity for massless particles. For massive particles, you can also introduce it in a very ultra relativistic situation. That means when the particle is moving very fast. Okay. ঠিক আছে, ঠিক আছে। হ্যাঁ, তোমরা বলবে, ব্যাস হয়ে যাবে। একটু চাই, আমারও ব্রেক চাই। একটু বসতে দাঁড়িয়ে দাঁড়িয়ে ক্লান্ত হয়ে গেছি। তুমি কি নতুন জয়েন করেছো নাকি? তোমাকে দেখিনি। কি নাম তোমার? মনীষা। এখন কি হোস্টেলে আছো? কিন্তু তোমাদের স্টুডেন্ট অ্যাটেন্ডেন্স তো কম, জানি না, ইন্টারেস্ট পাচ্ছে না বলে বেশিরভাগ লোকেরা, নাকি? অনলাইনে তো বেশি দেখছি না, 4 জন মাত্র। সকালে ছিল একটু বেশি। হ্যাঁ, তাহলে এখন তো কোভিড অনেকটা কমেছে, তোমরা এখানেই আসো না কেন আমি বুঝি না। মানে why are you trying to attend online classes? আমি বুঝি না। অন্তত যারা ইন্টারেস্টেড, আমি সবাইকে বলছি না। ওয়ান ওয়ে, যাওয়া আসা মিলে। তো তোমরা হোস্টেলে থেকে যাও না কেন? হোস্টেলে হ্যাঁ ডিসেম্বর থেকে উইকডেজে। হ্যাঁ এই আর আজকে তো হয়ে গেল কত, 13 তারিখ, 20 আর 27, দুটো স্যাটারডে নেব এইভাবে। তারপরে উইকডেজে অলিবাবুকে রিকোয়েস্ট করবো উইকডেজে দিতে, আমিও শনিবার দিন যাতে না আসতে হয় আর কি। মেট্রোর ভাড়া কত এখন দমদম থেকে দক্ষিণেশ্বর? 15, আগে তো এত ছিল না বোধ হয়। দক্ষিণেশ্বর যদি মেট্রো চালু হয় তো একটু সুবিধা হয়েছে না? তুমি বুঝতে পারছো? হ্যাঁ কি দেখো, আমি ইন্টারমিডিয়েট ইম্পর্টেন্ট স্টেপস গুলো দেখিয়ে দেবে, সব করা সম্ভব না, প্রচুর টাইম যাবে। আর এটা করা তোমাদের পক্ষে চামচ দিয়ে স্পুন ফিডিং হয়ে যাবে না। তোমাদের নিজে কিছু করলে হাতে জিনিসটা আসবে, তখন বুঝতে পারবে ভালো। নাহলে তুমি নিজে করো না, এমনি নোবেলের মতো পড়ে যাও, কিছুক্ষণ পরে দেখবে কিছুদিন পরে এগুলো ধোঁয়াশার মতন হয়ে যাবে, কিছু বুঝতে পারবে না। আর ফিল্ড থিওরিতে গেলে এইসব ম্যানিপুলেশন, গামা ম্যাট্রিক্স এর ম্যানিপুলেশন, এগুলো কিন্তু খুব লেফট অ্যান্ড রাইট এগুলো করতে হবে। ওকে, সবাই এসে গেছো? Okay, so far I was talking about this particular choice of polarization vector, which was convenient. I could go to the rest frame and orient my n, the 3 component of n, in the direction of z direction, and then could ask the question, what is the spin part of it? Okay. But suppose I don't want to go to the rest frame, whether I consider a particle, moving particle, and that too with very high speed, ultra relativistic. For this situation, it will not be, and I would like to ask the question, what is the component of angular momentum in the direction of 3 momentum? Obviously, if I were to go to this, since it's a massive particle, I can go to the rest frame anyway. Okay, but if I ask the question, what is the component of angular momentum in the direction of 3 momentum, it will be meaningless in the rest frame. Therefore, 3 momentum is 0, and there is no direction, right? So the only direction can be ascribed to it only when it is moving in a frame. Okay? So what I ask means, what I require here is to construct a suitable polarization vector, the same space-like unit norm, so that n square is equal to -1 is still holding, but the spatial part is proportional to the spatial part of the 4 momentum. This is a special choice. The question is, can we make such a choice where the spatial part of the polarization vector and vector, because n I am writing n mu component wise n0 n vector, right? So we require n vector is proportional to k vector, 3 component of the 4 momentum. Okay, so it is moving definitely. Otherwise, if it is 0 in the rest frame, it will not be. It will be meaningless statement. Okay, so the question is that, does there exist such a choice and mu so that this condition holds? The answer is the affirmative. The answer is yes, emphatic yes. Where I write down this particular choice in this following form. You see, the spatial component is indeed proportional to k. You can check that, left as in homework. Check eta bar mu is equal to -1. It is indeed space-like unit vector. Okay, and further, it is number one. It is orthogonal to K. N bar dot K is equal to 0. Is a 4 product. Mind that. By this I mean n bar 0 E, because K mu is, let me write K0 minus n bar vector dot K vector, right? And K0 is E, so n bar 0 E minus n bar vector dot K. You just substitute it here. N bar 0 is K mod K by M, and E minus n bar vector. This is n bar vector. This is n bar vector. This will be, just substitute here, then you will get, this will be 0. Check this. Okay. So then if you write, and this particular choice where these two conditions are fulfilled, okay, is called, this polarization vector is called helicity. So I can write with this choice, then third homework, you check P n bar lambda plus minus K is equal to identity plus minus sigma dot K by K vector. You can check this. So here also,
So,
yeah,
ইনটার সাথে কেটা 3 ভেক্টর ওয়াইজ প্রপোর্শনাল বাট 4 ভেক্টর ওয়াইজ অর্থোগোনাল, তাই তো?
right, 4 vector wise orthogonal.
ওকে,
That's correct. Okay. So here also you see this is nothing but here the projection, spin projection operator, just as you encountered in a non-relativistic case. So as in the previous case, Pn, so Pn projects onto positive helicity and positive energy states. This implies negative helicity, negative energy states. Just as happens in the previous case. Okay. Okay. Now you consider ultra relativistic limit. By helicity means projection in the projection of angular momentum in the direction of the motion. Three momentum. I have defined it such a way that three vector n bar vector, three vector, the special component is proportional to the k. So in the direction of the motion of the three momentum, they are the special part of the four momentum. Okay, so in that direction, it's a projection operator. Okay. So this is, you remember, sigma was my sigma 3 means appropriate sigma dot k, right? Sigma was, I introduced sigma. Remember, I have erased it. মুছে দিয়েছি। তো এটা যদি করো তাহলে এটা sigma dot k আসবে, and k দিয়ে ডিভাইড করছো ম্যাগনিটিউড, sigma dot unit vector একটা আসবে, special unit vector. So in the projection in that direction, in the direction of motion, okay, so in that direction, if you in the direction of motion parallel to the direction of anti-parallel, that will define your spin half or spin minus. Now according to that, it is a projection operator along the direction of motion or opposite to the direction of motion, depending on plus or minus sign. And this will project your energy eigenstates, positive or negative. Okay. So this lambda plus will project your positive energy eigenstates and positive helicity in the direction of motion, right? For negative energy, it will minus with the negative opposite direction, projecting in the opposite direction. Negative helicity states. Now I am considering ultra relativistic limit. By ultra relativistic limit, I mean that particles behave as if they are massless. Okay, as if that means, and if you boost it so much, that energy E equal to gamma m, and E is very, very high than compared to m. So you expect that whatever you learnt in a group theory class regarding the helicity of massless states, you can recover some of these things in this limit. Indeed, this happens. M by k naught, m by E, whatever I am writing, goes to 0. And k vector by k naught, that means mod of k by k naught, that means same as mod of k by E again, this goes to 1. That means energy and this thing becomes almost same, right? In this case, you can see that what happens, then eta bar mu, you check, will go to k mu by m. You just substitute and take the limit. Check, homework. It simplifies a lot. And then eventually the projector lambda plus k. So you see that m factor will disappear here, and you are left with just this thing. So you remember 1 plus minus gamma 5 by 2 to the chiral projector that I told you in the group theory class. In the chiral representation, you can see it automatically projects into psi L and psi R. Two component, recall that. So exactly you get these things. Okay. So you please derive all this. Okay. So with this I have introduced the projectors. Shall I continue with the web packet or কি বলছো মৌলি অনেক না মৌলির বোধহয় আরো খিদে আছে কফি খেয়ে এসছো তাহলে তো ভালোই হলো হ্যাঁ
স্যার
হ্যাঁ
স্যার বলছি এই আলট্রা রিলেটিভিস্টিক লিমিটটা আরেকবার বলে দেবেন, আমার নেট কানেকশন ছিল না।
না relativistic limit, ultra relativistic limit, mass becomes very small compared to the energy content. That you understand, right? Do you
না মানে
understand?
আলট্রা রিলেটিভিস্টিক লিমিট মানেটা কি?
Huh?
মানে আলট্রা রিলেটিভিস্টিক লিমিট মানে এটা কি?
হ্যাঁ মানে when the particle moves very very fast. If the
হ্যাঁ মানে
particle,
ভি সি এর কাছাকাছি।
হ্যাঁ vc এর কাছাকাছি, রাইট। হ্যাঁ আমি তো অবশ্য c equal to 1 ধরে কাজ করছি এখানে সর্বত্র, মানে v
হ্যাঁ
টা
সি
1 এর কাছাকাছি।
হুম হুম
If it moves very fast, you know E is equal to gamma m. Gamma is what? 1 by root over 1 minus v square m. So v is very close to 1. So it becomes close to 0. So it will diverge more or less in this limit. Means very, very large quantity. So m by e, if you or you just bring the e here, root over 1 minus v square is equal to m by e. You can write alternative like this. Now v going to 1, then m by e ratio goes to 0. Okay. You understand? Samajit?
হ্যাঁ স্যার।
Okay. So then you can show that 3 momentum magnitude will be very close to the energy. Okay. Because that will be gamma mv. 3 momentum magnitude is gamma mv. Okay. And v is close to 1. So energy and gamma m is energy. So it is E V. V is close to 1. So K and E are almost same. So K and E ratio goes to 1. Okay.
হ্যাঁ স্যার বুঝতে পেরেছি।
So this is your from special relativity. Okay. Huh? No, no, no. কোনো n এর আর কোনো picture নেই। n তো is particularly chosen this. In the n টা তো I have chosen. I have erased it. I have chosen in the direction of k. Z direction, in the direction of k. So I have chosen in that particular direction. So just work that out. কোনখানে এইখানে না এইখানটায় না ওটা কেটে যাবে we check it. I think it will just check it t by 2m বোধহয় থাকবে, right? From dimension analysis there should be m, right? But this p, just a minute, p n is gamma 2m gamma 5. Yeah, there should be some m, I think. Otherwise, dimensionally mismatch হচ্ছে। এটা dimensionless, এটাও dimensionless, k slash plus m by 2m, dimensionless. So it should be also dimensionless. So এখানে 2m থাকা উচিত, from dimensionless. Check it. Okay, right. So let me finish it here, and means if you have any question, you can ask me next time or in between also. আমাকে ফোন করতে পারো, তোমরা ফোন নাম্বার জানো তো? ফোন করতে পারো। আমি সৌম্যজিৎ বোস। সৌম্যজিৎ বোস তো আমি ভেবেছিলাম তুমি খুব অ্যাক্টিভিস্ট, ওই ফিজিক্স ফোরাম টোরাম করছো, ওই করছো, আমি ভাবছিলাম তুমি অনলাইনে খুব তোমার মোটিভেশন অনলাইন বা অফলাইনে এখানে ক্লাসে এসে তোমার বোধহয় আমি তোমাকে দর্শনই করিনি চর্মচক্ষে।
স্যার মানে আজকে যেতাম স্যার, শরীরটা খারাপ ছিল আর কি, সেই জন্য।
আচ্ছা, ঠিক আছে, ওকে দেন। তোমরা এটা একটু ইয়ে করে দাও, রেকর্ড করে দাও। ঠিক আছে, আমি তোমাদের বানানো আগেই ছেড়ে দিলাম। টায়ার্ড হয়ে যায়, দুটো ক্লাস 4 ঘন্টা টানা।